Hey, what's up guys? Today we're going to be learning how to solve systems of equations using the substitution method. Let's check it out. Alright, so I have a few examples lined up for you guys, sort of representing different scenarios that you might find yourself in. And I think later I'll probably make a video covering the concept of systems of equations, but for now we'll just stick with the method and work through some problems. So here we have a system of equations, which is just a fancy way of saying that we have multiple equations happening at the same time. Okay, and these are the equations of lines. These are linear equations. And we have y equals 10x and y equals negative 3x plus 39. And so how the method works, substitution, basically is if we have a variable solved for, which in this case we do, right? We know that y equals 10x, so y is already by itself. Then if you know that y equals this expression here, then wherever I see a y in the other equation, I can replace it with that expression, right? And that's what the substitution is. So since I know that y equals 10x, then if I see a y here, I can substitute 10x in for y. I can replace the y with the 10x. Okay, so I'm going to go ahead and do that. Okay, so as you can see, I've basically just rewritten this equation here, but instead of writing y here, I wrote 10x because I know y and 10x are the same thing, right? So that's what the substitution is. And what that does is this gives us an equation that is now in one variable. Notice how we're only dealing with x terms now, and there's no more y terms. And the reason this is significant is because we can actually solve this equation for an actual number. We can solve this for x, and we'll see what x equals. So to solve this for x, I need to get x on one side and by itself, right? So I want to add 3x to both sides here. Okay, so we have 13x on the left side of the equation and 39 on the right side of the equation. And then I can divide both sides by 13. And then I see that x equals 3. Okay, so now that I know that x equals 3, I can take this 3 and substitute it in for x into either one of the original equations. So this one up top is far less complicated. So I'm going to take 3 here and substitute it in for x, because I know that x equals 3. And so what I have is y equals 10 times 3, which is 30. And so your solution to the system is the xy coordinate pair. So your x coordinate is 3, and your y coordinate is 30. So this coordinate pair is your solution to the system, and what that means is that it's the only ordered pair, it's the only xy pair that will satisfy both of these equations. Okay, there's infinitely many xy pairs that'll satisfy this equation, and there's infinitely many xy pairs that'll satisfy this equation, but there's only one xy pair that will satisfy both of them. And you can check this by substituting these values into the equations, right? 10 times 3 does in fact give me 30, and negative 3 times 3 is negative 9, and negative 9 plus 39 is in fact 30. So we can see that this ordered pair does satisfy both equations. Okay, so that's sort of the first scenario. So now this example is a little bit different. Now it still starts off sort of the same way in that we already have one of the variables solved for, which is good. these are the types of examples where substitution is a really good method because you already know what one of the variables equals. So again, since I know that y equals negative 4x, wherever I see a y in the other equation, I can substitute negative 4x in for that because I know that y equals negative 4x. And so what I'm going to do is I'm going to copy down this equation exactly, except instead of a y, I'm going to substitute the negative 4x. Okay? So I have the 2x minus 5 times y, but I know that y is negative 4x, so I'm going to say minus 5 times negative 4x. Okay, now this needs to go in parentheses because I'm multiplying the 5 by that entire expression, and that equals 44. Okay, so again, I just recopied this equation down, but I substituted the negative 4x in for y. And now I can just simplify the left side of this equation. So I know that negative 5 times negative 4x is a positive 20x. And now I can combine like terms. I know 2x plus 20x is 22x. And then of course I divide both sides by 22. And I see that x equals 2. But again, I'm not finished. This is just the x coordinate, right? So now that I have my x coordinate, I can go ahead and substitute this into either equation for x, and that'll spit out the y value. So this one, again, looks less complicated. So I know that y equals negative 4 times whatever x is, but I know that x is 2. And so I see that y is negative 8. And then again, I'll write my solution as the ordered pair 2 comma negative 8. And again, you can check this. You can substitute 2 and negative 8 into this equation for x and y respectively and see that it works, right? Negative 4 times 2 is in fact negative 8. And 2 times 2 is 4. And then negative 5 times negative 8 is positive 40. And 4 plus 40 is 44. So it checks out for both equations, as it should. And so this is the only ordered pair that'll satisfy both of those. And now for the third situation I have outlined here, this is sort of where substitution, depending on your preferences, may or may not be the best method to use, and you might prefer to use a different method. But just in the event that you have to use substitution, it's good to see this. So the reason this is tricky for substitution is because we don't have a variable that's isolated in either equation. Okay, so x nor y is solved for up here, and x nor y is solved for in this equation. So we have to do a little bit of work. We actually have to solve one of the equations for a particular variable. So I'll take this top equation and I will solve it for x. Okay, so how do I get x by itself? Well, I'm going to add 3y to both sides. Okay, and so my new top equation is going to look like this. X equals 4 plus 3y. Okay, and now I have an equation that's solved for a variable. So now I can proceed with the substitution just like the other two examples. So since I know what x equals, I know x equals this stuff, right? The 4 plus 3y. So in my other equation, wherever I see an x, I can replace it with 4 plus 3y, right? That's the substitution I can make. So I'm going to rewrite this equation here. But instead of writing 4 times x, I'm going to write 4 times the expression that x equals. Okay, and so this all has to go into parentheses. So 4 times the quantity 4 plus 3y. Right? And just like the last two examples, the substitution, as we see now, turns this into an equation with just one variable, and that variable is y in this case. So we can solve this for y and get an actual number. So we see we have some distributive property involved here. So 4 times 4 is 16, and 4 times positive 3y is a positive 12y. And then I have my minus 5y equals 23. And then you just simplify. Combine like terms. We have a positive 12y and a negative 5y. That's going to make a positive 7y. And then we can subtract 16 from both sides. And so we see that 7y equals 7. And then we divide both sides by 7. And so we see that y equals 1. And just like the last two examples, now that we know what y equals as a number, we can substitute that into either equation for y. So the top one probably looks a little bit simpler, or I could even substitute it in for this one, since we know this is an equivalent equation to the original. So I'll just go ahead and take this one and substitute it into this equation. So we have x equals 4 plus 3 times whatever y is, and we know that y is 1. And so we get 7. And so your ordered pair, right, the solution is going to be 7, 1, because remember, x is 7 in this case, and y was 1. So this is the only ordered pair that will satisfy both of these equations, and again, you can check that if you need to. But that's basically all there is to it. All right. And with that said, it's been demonstrated.